This is Caleb.
This is Daniel.
And Anush.
And this is our final project on facial emotion recognition, titled Mixed Feelings, Recognizing, Representing, and Interpolating Human Emotions. The facial recognition goal became widely popular back in 2013 in the advent of a popular competition on Kaggle. An important aspect of human communication is body language. Tone and emotion can completely change the meaning of what someone is saying. This is especially important for social robotics and human-computer interaction. A more niche application might be something like driver fatigue surveillance. The FER 2013 dataset is a simple standard for the facial recognition problem. It consists of 28,709 48 by 48 grayscale images, each labeled with a single emotion: anger, disgust, fear, happy, sad, surprise, and neutral. However, upon exploring this dataset, it begins to show its age. Happy images are heavily overpopulated, while images showing disgust are nearly non-existent. Additionally, a few cherry-picked examples show the low fidelity of samples in this dataset, with mislabeled images and non-face images masquerading as having emotions. Beyond the simple mislabeling of images, we found 91 duplicate images in the test set, many of which have mismatched labels. Still, we decided to train a baseline model on this entire dataset, warts and all. We used a standard for low-resolution image classification, a convolutional neural network with 3 convolutional layers, including a max pooling and 20% dropout, followed by 2 dense layers and a softmax activation. Labels were decided by the most probable output. The model achieves an underwhelming top accuracy of 54% and shows exceptional confusion on emotions other than happiness.
Taking a step back, we next explore PCA as a baseline for unsupervised learning on this dataset. Specifically, we are projecting the images which lie in a 2,304-dimensional space onto a 2-dimensional space that captures maximum variance. It's important to note here that PCA will capture variance due to many different factors, such as head pose and overall lighting. Since such features are generally more macroscopic than features contributing to variability in emotion, we expect that the variance captured by the first 2 PCs will not capture emotion well, and this is exactly what we observe here. To then begin exploring whether preprocessing may improve emotion detection, we start by performing edge detection. For this, we use the Carnegie algorithm, which at a high level first smoothens the image using a Gaussian filter and then is able to identify intensity gradients to pick up edges using a double thresholding process. Using then a training set with edge-detected images, we train a convolutional neural network to predict emotion. We also explore the radon transform, which essentially represents images as a series of projections. Specifically here, we project the image onto a line at a fixed angle and then repeat the projection at many different angles. If then the projections are appended together to form a single 2,304 element vector, the Fourier transform of this series would uncover frequencies characterizing the data. Crucially, our hypothesis here is that the uncovered frequencies must be rotationally invariant, that is, regardless of by how many degrees a face is rotated, the computed frequencies should be about the same, since this simply corresponds to a phase shift in the radon transform data series. Preliminary analyses show this method does not offer any significant benefits in representing emotion, but a full analysis is pending. Finally, to explore whether a framework could be developed that is rotationally invariant, we next created an augmented dataset of randomly rotated images. Specifically, we augment the original dataset with a second copy of the training set in which each sample is randomly rotated by an angle between 0 and 180 degrees. We hypothesize that when training a CNN with the dataset, the network will learn to predict emotions in a rotationally invariant way. In general, we see that the pre-processing methods we have explored do not perform well in classifying emotions correctly. Both edge detection and data augmentation appear to perform approximately the same, if not worse, than the CNNs trained on the raw image dataset. After our preliminary analyses using the FER dataset, we observed some major issues with the quality of the data. Firstly, many images in this dataset are not even of faces. Also, in many cases, faces appear to be at a sideways angle rather than front-facing. Finally, one of the most important points to be made is that the single emotion classification problem itself is a poorly defined task, since human emotion can often be a mixture of multiple different emotions. This ambiguity is likely reflected too in the interpretation of emotions from facial expressions by another person.
FER Plus is an updated labeling of the FER 2013 dataset provided by Microsoft. Each image has been classified by 10 crowdsourced individuals, creating an emotion probability distribution rather than a one-hot label. This dataset immediately improves the baseline model performance by almost 20% and outperforms Kaggle competition winner in 2013 in terms of validation accuracy. However, the confusion matrix is similar to the model trained on the original FER dataset. This leads us to our first novel conclusion. Multinomial and even probabilistic representations of emotion are insufficient to capture the nuance of human emotion. This is succinctly understood as the idea of mixed feelings.
Based on our observations, we decided to explore new methods for learning better latent representations of human emotion. We mainly worked with three variants of autoencoders: the standard convolutional autoencoder, variational autoencoder, and beta variational autoencoder. An important observation is that these data-driven representations tend to capture the largest visual sources of variance in images. For example, head orientation, skin tone, background, illumination, etc. The first plot on the right shows the results of running PCA on the lane representations learned by a standard autoencoder, where the points are labeled according to emotion labels. It is possible to see that the variance captured by the first two principal components failed to extract patterns related to emotion. To induce correlation between the lane space and emotions, we added an emotion decoder to the autoencoder, so that the model is trained on both the reconstruction and the emotion classification losses. The second plot on the right is a diagram of a standard autoencoder with the emotion decoder. In the interest of time, we focus on the beta variational autoencoder model with an emotion decoder for the results. VAEs learn a distribution over the lane space to obtain smooth representations of the input. A Beta-VAE slightly differs from a standard VAE in that it can flexibly induce disentanglement, which can control how much a lane feature is sensitive to the generative factors of our data. More specifically, the beta term in the evidence lower bound determines the extent to which regularization via the prior is cast on the variational family. When the beta term is tuned properly, disentanglement can improve interpretability of the lane dimensions and allow us to generate new examples in specific ways. For our problem, the intuition, therefore, was to capture disentangled visual patterns that correlate with different emotions. It is also worth noting that learning such features could potentially allow us to generate images with correctly aligned faces. This can be highly beneficial given how much variation there is in head pose and makes the classification task difficult for the model. Jointly training for the variational objective and categorical cross-entropy, we obtained a test classification accuracy of around 64%. When we looked at the latent representations directly, interestingly, we observed that certain dimensions seem to show some amount of correlation with emotion. Latent feature 91 in particular generated faces with different expressions when it was modified, translating an originally neutral image into new images that appear surprised and happy. While this isn't the case for every latent feature or input image, it's certainly an interesting result, and we plan to explore this direction further. We are also considering extending the VAE approach to model the lane space as a Gaussian mixture. Specifically, we can think of learning a smooth multimodal distribution of lane variables to do unsupervised clustering of the images according to their emotions. Further adjustments need to be made in the optimization step, as the reparameterization trick cannot be used for discrete variables, but we think it would be an interesting model to try out. Additionally, to improve our models in emotion extraction and classification, we are interested in extending the approach to a multitask learning framework, where a localization decoder that maps the images to bounding boxes or facial landmarks can be added. Assuming we can obtain labels for such tasks by using pre-trained deep neural networks, we expect that the model will perform well, a lot better at ignoring background noise and identifying facial features to focus on, which are most important for inferring emotion. For future directions, here is a list of all the things that we want to try out. First, we want to try using discriminative models of classification on the low-dimensional encodings, for example, KNN or K-means, to detect emotion. We also want to develop improved data pre-processing methods with a focus on face alignment and outlier detection. And as mentioned before, in terms of generative models, we want to try out Gaussian mixture variational autoencoders. And we also want to improve the CNN feature extraction methods with a focus on localization and facial feature extraction.
Thanks for listening.